This is part 6 of the series Calculus Prerequisites, and I'm going to begin this part with a quick review of radicals. Before I get into the details of working out radical problems, I would like to just do an overview of what a radical is. Remember that radicals are simply values to a rational exponent. So here we have the square root of 3, and if you want to look at that from a slightly different perspective, the square root of 3 is actually 3 to the 1/2 power, where the 2 in the bottom here is the index that goes in the radical symbol here. Down here we have 3 to the 1/3 power because this is a cube root. So if I wanted the cube root, so the cube root of 2, that's 2 to the 1/3 power, and so on. The index always goes in the denominator. So when you're looking at a rational exponent, the numerator is the power, the denominator is the root or index. Now, that's one of the reasons why the properties of radicals are the way they are. Here, when we have the same index, this is in essence just like if you had something like this. If you had x squared minus x squared. This is x squared minus x squared, which is 0. Here we would have negative 5x squared minus 3x squared. So it would be simply negative 5 minus 3, which is negative 8x squared. Well, in this case, we have negative 5 times 3 to the 1/2 minus 3 times 3 to the 1/2. This value is taking the place of the squared term. So we have 5 of these minus 3 of these. Think of this as 5 rocks minus 3 rocks. We have negative 8 rocks. I don't care how you look at it, it doesn't really matter. But if this radical is the same, these things can be just simply added or subtracted together. Now, we look down here, we have the same process. We know that we have 2 square roots of 8 minus 1 square root of 8, which gives us the square root of 8. Now, you may think, oh, we're done. But in actuality, this is just the first piece. There is a form working with radicals, simplest radical form or reduced radical form, whichever you want to call it. And what you would have to do is simplify the value inside the radical. The value inside the radical, remember, is called the radicand. And the easiest way to do this is using a prime factor tree. Remember, prime numbers are numbers other than 1 that are evenly divisible by themselves and 1. So the first prime number is 2. So we always start with 2. And we say, does 2 go into 8? Yes, 2 goes into 8 4 times, and you keep going. 2 is still the prime number. Does 2 go into 4? Yes, 2 goes into 4 2 times. So here we have our prime factors of 8. So that means that the square root of 8 equals the square root of 2 times 2 times 2. And 2 times 2 is simply 2 squared times 2. Now, one of the other basic properties of radicals is that the radical of a product is equal to the product of radicals. So this is the square root of 2 squared times the square root of 2. So this is a basic property of radicals. And the square root of anything squared is that thing. And if you work this out, 2 squared is 4, the square root of 4 is in fact 2. So anytime you have a pair of values under a square root symbol, under a radical with index 2, that pair of 2's comes outside the radical as 1, 2. So in this case, this becomes a 2, and we still have the square root of 2 left inside. So the square root of 8 is the equivalent of 2 square roots of 2. If you put that in your calculator, you'd see that they're the same value. So this expression simplifies to this. And once you get practiced at this, if you're not already, if you've gotten a little bit weak from non-use, practice this a few times and it'll be pretty automatic for you. But just look at these values. Any pair comes out of a square root symbol as one of those numbers. Down here, if we have 3, 3 would come out with an index of 3. If we had a fourth root, 4 numbers would come out, and so on. All right, so let's go down to look at this one. Now, I had said that the radical of products equals the product of radicals, and the reverse of that is the product of radicals equals the radical of products. So here I have the same index for two values, 3 and a 3. And so this product of radicals can be rewritten as 3 times 9. The cube root of 3 times 9. Now, you know that 9 is simply 3 times 3 times 3. So that's 3 times 3 times 3. So that's the cube root of 3 to the third. And so as we set up here with an index of 3, any 3 numbers under the radical comes outside as one of those numbers. So this is actually 3. This is the same as saying the cube root of 3 to the third. And the way you can, another way to look at this is this index cancels out that exponent, left with the radicand itself inside. Any way you want to look at it, it works out the same way. All right, let's move up to this one. Here we have the square root of 6 times the square root of 2. This gives us the square root of 12. And if we try to simplify this, 2 is the first prime number, 2 and 6. 2 goes into 6 3 times, so 2 and 3. So one pair of 2's comes out, so that's the same as 2, and we still have the 3 inside the radical, so that's 2 square roots of 3. Now this next one's an interesting mix, so let's start with the left piece. So we have negative 3, and this one simplifies to, we have 2 and 6, 2 and 3. So this is 2 square roots of 3. So it's negative 3 times 2, which is negative 6 square roots of 3. This one is plus 3 square roots of 3. And this, we have 2 and 10, 2 and 5. So we have 2 comes out, 2 times 3 is 6. So that's plus 6 square roots of 5. Now here these two can be combined, and we have negative 3 square roots of 3 plus 6 square roots of 5. And before I move on, these two problems bring to mind an interesting idea. Sometimes when we're working with things in calculus, we're going to need to work with strictly exponential forms. And in that case, when you have something like this, we can convert this into a purely exponential form as opposed to a simplified radical form. If you look at this from an exponential standpoint, this is 2 to the 2 halves power, or 2 to the 1 power, the power of 1. This is 2 to the 1 half power. When we multiply exponentials with the same base, we simply add the exponents. 2 halves plus 1 half is 3 halves. So this is equal to 2 to the 3 halves power. So we can convert these values to purely exponential forms. Same thing over here. We have negative 3 to the 2 halves times 3 to the 1 half power, and negative 3 to the 2 halves times 3 to the 1 half is negative 3 to the 3 halves power, and then we just add this piece in, plus 6 square roots of 5. you could put 6 times 5 to the 1/2. There's no point in combining these into exponentials because this one is not with the same base. So it's only when you have the same base that it becomes an issue like there. So if you want to work with pure exponentials, there's the conversion. And if you want to work with mixed, it's this one. So let's work on the last one here. And in this case, we want to get this down to some common element if we can. So let's do square root of 24 first. See what we got here. That's 2 and 12, 2 and 6, 2 and 3. So it's going to be 2 square roots of 6 because one pair of 2's comes out. So that's 2, and we have the 2 times 3 left. So that's 2 square roots of 6. And then this is the square root of 3. And this is 8 again was 2 square roots of 2. So you should remember that from over here. And so now, since these are being divided, this can go away. So we have the square root of 6 times the square root of 3 over the square root of 2. 6 times 3 is simply 18. So that's the square root of 18 over the square root of 2. And now we have a situation where just as we had the product of radicals equals the radical of products, the quotient of radicals equals the radical of a quotient. So 18 divided by 2 is 9, and that's just 3. Now you could have simplified this whole thing if you have a calculator with you. That's all you had to do if we just kind of loop around over here. This is the same as saying the square root of 24 times 3 divided by 8. So you could work this out in your calculator and you would have come out to the square root of 9, which is 3. Either way you want to look at it, you can work it through. I just wanted to show you a various set of ways to do this so that you can get practiced at it. All right, now we're going to move on to exponents. Now for exponential rules, let's take a look at the first one here. If you have a value to a power raised to a power, remember that the rule is you always go down one order of precedence. So here we're raising to a power, so the one down is multiplication, so we multiply the exponents. That's 4 times 3 halves, which is n to the 12 halves, which is n to the 6th. Same thing for here. We have 3 halves times negative 2, so that's p to the negative 6 halves, which is p to the negative 3. And anytime you have a negative exponent, it's not completely simplified until the negative is gone. So that's 1 over p cubed. Here we have two values with the same exponent. Since we're raising both of these to the same exponent, we can say that this is simply 4 over 6 to the third, which simplifies to 2/3 to the third. And this cube applies to both. 2 cubed is 8. 3 cubed is 27. So there's your final result, 8/27. So 4 cubed divided by 6 cubed is 8/27. Let's move on to this one. Here we have the same base. And now, with the same base, we can say that this is just 3. 3 minus 5. When you're dividing exponentials with the same base, you subtract. So the one down from division is addition and subtraction. If we were multiplying, we would add. If we're dividing, we subtract. So this is 3 to the negative 2, which is 1 over 3 squared, which is 1/9. Now you could probably have gone from here to here in one step, but I just wanted to show you the progression. All right, well, we're going to finish these next two in the next video and continue on with other forms of exponentials. So I will talk to you in the next video.